All right, this is going to be on lesson 7 in quadratics. This is unit 3A. Today we're going to talk about imaginary letter I and imaginary solutions. And then part 2 of this, which is lesson 7A notes, is going to be on the real number system. So let's get started. Up until this point, what we've really done is we've looked at graphs of parabolas, and when they cross the x-axis in two places, then we end up with two solutions, okay? If the graph touches the parabola, touches the x-axis in one place, we have one real solution. In this case, the last case, we have 0 real solutions because we do not touch, okay? And when it does not touch, prior to this, we had always said no real solution. Or sometimes I'd even use that symbol 0 with a line through it for no solution. However, this is where we're going to pick up and kind of explore just a little bit more. This will now have two imaginary solutions. So, as background, let's just review. When you take perfect square roots, you're basically using a radical symbol. Okay, this is a radical symbol. And when you don't put a number in the corner, it's implied or understood to be a 2. So technically you're taking the second root or a square root of a number. And we take a lot of square roots. That's by far the most common. You can also take a third root. For example, the third root of 8 actually means what number times itself 3 times gives us 8. And it turns out 2 to the third power equals 8. So the third root of 8 is 2. Okay? So we can use that radical symbol, which is simply that this part right here, that's the radical symbol. And all of these that we're doing today are square roots. So we're basically saying what number times itself twice is 16? Answer is 4. What's the square root of 25? So it's like it comes out as a 5. All right. What number times itself twice is 100? And that would be 10. So 10 comes out. 10 is the answer to the square root of 100. What's the square root of 400? If you take your calculator and check it, it turns out 20 times 20 is 400. So 20 is the factor multiplied by itself twice that gives me 400. When we do square roots of fractions, you can look closely and see it looks like the top part is a perfect square and the bottom number is also a perfect square. So I can actually take the square root of 25, and separately I can imagine taking the square root of 36, and my answer becomes 5 over 6. 16 square root of 225th is 4. Square root of 225 is 15. Answer is 415. Okay, now let's jump in and start looking at what it takes to be imaginary. It says equations such as this in the past. All right. So if I were to pull over x squared plus 1, set that equal to 0. When we did square roots method, the very first thing we did is had to get x squared by itself. So to do that, I would subtract 1 from both sides, and I would end up with x squared equal to -1. And so the square root method basically says take the square root of both sides as my second step. The square root of a square actually gives me x, but the square root of -1 is a problem because when I do square root, okay, square root of -1, I do not have the bar, this is an older version, it simply says quit non-real answer. Gives me an error. And that's because up until this point we did not have a solution. Okay, now we do. As of today, now we do. So we used to say no solution. This used to give us an error. And for the first time today, we're actually going to find a solution. The imaginary unit, I, is defined as the square root of -1. This is useful when working with square roots of negative numbers. The pure imaginary number is written in the form a plus bi, where a is the real part, or the real number, and the bi at the end is the imaginary part. Okay, let's take a look and see how we are going to apply this for our purposes. All right, I'm going to take the square root of -9, and I'm going to basically break it down. Okay, the square root of -9 is going to be broken down into -1 times 9. Okay, I can think of that as the square root of -1 times the square root of 9, and both of those actually work out. The square root of 9 would come out as a 3. The square root of -1 By definition from what's above means it's going to come out as the imaginary letter I by definition. So the square root of -9 is 3, little letter I. Square root of 196. It's going to be -1 times the number 196. Now, separately, the square root of -1, we just learned, comes out as little letter I. 196 is a perfect square root. If you check, 14 times 14 is 196, so this is going to come out as a 14. The answer would be 14I. So basically what we're doing is we're taking the square root of those perfect squares, we're pulling it out, and if it has a negative, we're thinking of that as -1. The square root of -1 produces the I. Number 3, square root of -1 times 5. Turns out this time 5 is not a perfect square root. So I'm kind of stuck with a little bit of a dilemma. I can actually still pull the square root of -1. That is still by definition little letter I. So it's like I've pulled out the I. But the square root of 5 is not a perfect square root. I do not want you to use your calculator. I do not want it changed to a decimal. And the reason is, for our purposes, when you have an imaginary solution, that is nowhere on a number line. So I don't need to express that as a decimal. So I want you to keep the square root, and I want you to keep the 5 under the square root. The I moves out front, so it's I, square root of 5. All right. Number 4, square root of -80. Again, think of that as -1 times 80. Is 80 a perfect square? Man, just misses. 81 is a perfect square, but not 80. So what I can do is I can move out the I because of the -1, but the 80 needs to stay. So this is going to be I moved out. The 80 must stay under a square root. So I square root of 80. 32, not a perfect square root. -1 times 32. The -1 can come out as an I. 32, though, is not a perfect square root. 36 is, but not 32. So at the end of the day, I came out. That's the only thing that came out. I still have a square root, and I still have a 32 under the square root. Okay? So I hope you're kind of picking up on what I need you to do. Now, there is a way to simplify the square root farther, but for our purposes, for our core content, North Carolina, we don't need to do that at this time. Square root of 192, again, -1 times 192. 196 is a perfect square, but not 192. So that's going to come out, no, excuse me, that's not going to come out. Square root of 1 will come out as an I. I is outside, square root. 192 stays in the square root, and that's my answer for that part. So hopefully you're picking up on the fact that we now are going to be able to do negative square roots. Now, I just want to show you a little tidbit with the calculator. Okay. If I was to actually play with it just a little bit, at the top of the key next to the second button is a mode key. If I click the mode key, this calculator is capable of a lot. What I want to do is I want to go down to where it says the word real, and I want to change it until I can move it over until it says A plus BI. And if you press enter, what you just done is you changed the way the calculator is going to give you answers. Always before it's given me real answers. If it can't give you a real answer, it says error, non-real answer. Now I'm going to say, hey, it's okay. Give me imaginary answers. So I'm going to second and I'm going to quit. So now if I retype in square root of -1, I actually now see that it shows an I. So I just want you to understand that your calculator works that way. So if I were to go back and look again at our first example, square root of -9, it actually simplifies to 3I, just like we practiced. Now, if you do try to take, like for example, square root of -5, it will change the square root to a decimal, and it will put the I at the end. We do not need you to do that. If you are going to look for your answer on a multiple choice test, the square root will probably still remain over the 5. They are very likely not to change that front part to a decimal. If you were to write this decimal answer for me on a quiz, probably would not count it wrong, but that is still not going to be how you're going to see it probably in multiple choice questions. Just wanted to show you that. Okay, let us see what happens when you solve. We're going to revisit the square roots method. I think that's written on your notes. So if we do this by square roots method, the very first thing that I want to do is I want to get the x squared by itself. So to do that, if I want to get x squared by itself, I'm going to subtract 81 from both sides. I get x squared is equal to negative 81. Square root method, the very second step says take the square root of both sides. Because I don't want my x squared, I just want x. Well, this undoes the square. I get x back. Remember, square root of a square undoes it. Get x. The square root of negative 81 can be expressed as negative 1 times 81. 81 is a perfect square. So 81 can come out as a 9. The negative 1 square root can come out as a I. X equals 9I. But there are supposed to be two solutions. So the third thing I always mention is don't forget plus or minus. Okay. Please understand that this solution actually represents a parabola that's actually shifted up 81 units. And there's nowhere close to the x-axis. So, you know, if you kind of sort of imagine if there was a ghost hovering over the x-axis, then maybe it would hover over approximately 9 and negative 9. I'm not sure exactly how I want you to think about that, but this is what we're trying to do. We are solving now for negative square roots of negatives as little letter i's. Okay, number 8. First thing I'm going to do is subtract 9 from both sides. I have 2x squared remaining equal to negative 8. To get x squared by itself, I'm going to divide out the 2. X squared is equal to negative 4. Take the square roots of both sides. That allows me to get my x back. Square root of negative 1 times 4. What happens is the I pops out. And if I look closely at 4, sure enough, it is a perfect square root, so out pops an I. X equals 2I. Don't forget what? Plus or minus. It's just that I don't want you to forget that. All imaginary answers should have two solutions. Number 9. We have a few examples. Number 9. First thing I want to do is subtract 15 from both sides. 4x squared equals negative 24. I need to divide out my 4 so that I get x squared by itself, negative 6. I need to take the square root of both sides. X and square cancel, I get x back. Square root of negative 1 times 6. 6 is not a perfect square. So I'm going to have to leave the square root over the 6. But the I comes out as a, or excuse me, the negative 1 comes out as an I, which stays right in front of the square root. And when it says don't forget plus or minus, make sure that you put it in front of the I. Okay, if you put it in between, that actually represents a whole different answer. Okay, so do not do it that way, plus or minus I square root 6. Number 10, subtract 13 from both sides. X squared equals negative 12. Take the square root of both sides. X is equal to square root of 12 is not a perfect square root. So I cannot take 12 out. So square root has to stay with 12. But the negative 1 can come out as little letter I. And don't forget what? Plus or minus. Okay. So we're solving for x. Number 11. First thing I want to do is I want to add 5 to both sides. I get 3x squared equal to, I believe, negative 441. When you divide by 3, I believe that is, oops, sorry about that. Divide by 3, x squared is equal to negative 147, square root of both sides. 147 is not a perfect square. 144 is a perfect square. So I have to leave the square root of 144. The negative comes out as little letter I. X is equal to plus or minus I times the square root of 144. Number 12, first thing I want to do, and I notice I have a fraction. I can deal with that. A negative 2/3 x squared is equal to, I believe, 18. Now, a lot of times what you need to do is you want to think about the reciprocal of your fraction. When you have a 3 on the bottom, that's like dividing by 3. So I'm going to times by 3 on top. If you have a 2 on the top, that's like timesing by 2. So the opposite of that is I'm going to divide by 2. So basically I'm taking my fraction, flipping it upside down, and in order to make this side become positive, I need to multiply a negative times a negative to make this become a positive. My 3's cancel, my 2's cancel, and I just end up with x squared. Well, if I multiply this side by negative 3 over 2, then I have to come over here and multiply this side by negative 3 over 2. So you can consider 18 to be over 1, multiply the numerators, divide by 2. I believe you get negative 27. So, square root of both sides, x is equal to negative 1 times 27. 27 is not a perfect square. 25 is, but not 27. Square root of 27 must remain. This comes out as little letter I, plus or minus. All right, and at this time, if you want to go down to where it says try these, oops, then you can go down. I was working on those earlier. Those are the answers to the first 4 or 5. All right, we are getting ready to transition to the second part of lesson 7, which is on imaginary numbers and the real number system. We just spent several minutes going over solving when we have imaginary solutions and pulling out little letter I when little letter I is the square root of negative 1. That's about as far as I need to dive into the pool of you learning all you can about square root of negative 1 being little letter I. You just need to be exposed to it. You need to know what it is. You need to know how to write it. Okay. I'm going to move on then to lesson 3A. This is still kind of sort of one day's worth of lessons. Lesson 7A, still part of lesson 7, but it kind of puts it in context with where does imaginary numbers fall in terms of the real number system. So just to kind of give you a big broad overview, if you could think of every number in the world, all the numbers of the world, well, up to this point, every number that you could think of would be considered a real number. Even if it's a fraction, even if it's a square root, even if it has pi in it, no matter what kind of number you have, you could actually put it in the calculator, get a decimal version of the answer, and usually locate that value somewhere on a number line. Okay? But as of today, as of just a minute ago, we now know that there are a few numbers in the world that have this little letter I in it. So now some of our numbers in the world are going to be considered imaginary. Okay? Now, I'm still giving you a big broad overview, and we have notes on the list that's going to take us through this lesson. If you have a real number, again, these are numbers on the number line. You can actually have two branches of reals. You can have a branch that is rational, and I usually think about people who are rational. You can reason with them. You can talk to them. You can make them understand your viewpoint. They will listen. They'll take it in, and they will be calm and considerate. And then there are irrational people. People who you think you just talk to your blue in the face and you never really accomplish anything. Like they deliberately don't want to understand what you're saying. They're very irrational. They get loud. They get argumentative. So you have numbers. You have numbers that are nice numbers. Numbers that can be fractions. Those are our rational numbers. Okay. Like 2/5, that's a pretty nice fraction. That turns into 0.40. You even have 1/3. 1/3 turns into a pretty decent decimal, even though it repeats the 3. Irrational numbers are like square root of 2. Okay, I think that's 1.414. I don't even know all the numbers, but it's a square root number that doesn't end. It's not as nice. So we have rational numbers. We have irrational numbers. From that point on, you can actually break the rationals down into integers, and then from that point you can break integers down into whole numbers, which means you have no negatives, and then you can break that down on into further into what we call the counting numbers. Excuse me, I think it actually classifies them as natural numbers, and I think of them as counting numbers. I learned to count, when I was teaching my children, I learned to count with number 1. So we start with 1 of something, 2 of something, 3 of something. Those would be considered natural numbers or counting numbers. But this is kind of like a big concept map of where our numbers are now, the numbers that we've grown up with, the numbers that we use in our lives. And as of today, we now can add this new branch of our numbers called the imaginary numbers. All right, to put this all into context, the real number system is divided into these subcategories. These are the same, I think you'll recognize some of these same numbers. Real numbers, rational and irrational. We have integers, we have whole numbers, and we have natural numbers. So this is just a little bit more information regarding each of the subgroups, okay? All right. Let's talk, oops, it was a little too far. Let me clear that. All right. This would be a page where I would hope that you would take a minute to write the notes as I put them in here, because I'm going to try my best to clarify how you can distinguish between the different groups. So if I write it down, I expect that it's something you definitely need to know. All right, let's talk about real numbers. And I think this is pretty easy to think about. This could be any number on the number line. Even if it's a decimal. 3.14 is approximately what pi is, or the pi value 3.14 ... I could usually go to a number line and at least approximate and put it on there. So any number on a number line is considered a real number. But if you're not real, then you might be imaginary. So imaginary numbers must contain little letter I. Okay? Must contain little letter I. Or be a term that would become an I. For example, like, what's the square root of negative 25? Well, square root of negative 25, we just talked about this in the first part of this lesson. 25 is a perfect square. That part can come out as a 5. Now we know that that negative could be considered as negative 1 times 25, and that part can come out as an I. So basically, that would result in 5i. So if it's an expression that would result in an I, then it has to be considered an imaginary number. Otherwise, you know, it's definitely not real, because it would give me an error on my calculator. So when we say like 2i, or if we say 3 plus 2i, or if it just has an I in it, pretty much to be imaginary, it has to have an I in it. Okay, so that's pretty much what it has to have. Now, from the real numbers, we're going to break this down into rational and irrational. Kind of talked just a small bit about that already. Okay, your rational numbers can be expressed as a fraction. Can be expressed as a fraction. Some fractions are nice. Like I mentioned, 2/5. If you take 2/5, okay, if I grab my calculator and I check 2 divided by 5, it turns out that's 0.4. And I would say that that 0.4 ends. It definitely doesn't go any farther. You can put a 0 if you want to, but 2/5 is actually 0.4. That's definitely a rational number. Even 1/3. Okay, let's take a look. 1/3. 1/3. 1 divided by 3. Now, if you'll count, it turns out there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 10 decimal places, or at least 10 numbers across there. In this case, I have 10 0.3s. Okay, that is actually a number that repeats over and over. So I could actually put that as 0.3, and to show that it repeats, I hope you're familiar with that little bar. That little bar means, hey, it repeats that 3. So if you'll notice that we have a border down here, so I'm going to still be within my rational numbers. I'm going to add this note also. As a decimal, okay, it ends nicely, like 0.4 ends, or it repeats. And it might be sometimes that it repeats like 0.333, or it could even repeat like a 0.15. You know, there might be a case where it might be 1, 5, 1, 5, 1, 5, 1, 5, 1, 5. The 1 and the 5 both repeat, so you could put a bar over both. But as a decimal, those fractions could either change to a decimal that ends or repeats and still considered to be a nice rational number. Okay. Now that doesn't mean rational numbers can also be 2. 2 can be expressed as over 1. So 2 is still rational. Negative 5.2, still rational. Square root of 25, rational. 2/3, rational. Negative 1/2, rational. So there's lots and lots and lots and lots and lots of numbers that are rational. All whole numbers, all regular numbers are all going to be. You could always put a 1 to make them be rational. Now let's contrast that to irrational. I'd like you to find on your calculator, it's right here above the up arrow key, right below the clear key, is the pi key. And there's the pi. Remember the little letter pi. If you press enter, it turns out that I see 3.14. When I count, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. Now, I hope that you know that after the 9th decimal place, there's actually a lot more numbers out there. Students forever in colleges, professors, different people who are fascinated with this concept of pi, which is the ratio of the circumference of a circle divided by its diameter of the circle. They have actually taken this out to hundreds, I believe hundreds of decimal places with some of those large supercomputers, and they've never found an end to pi or a repeating sequence of numbers of pi. So it's not a nice, neat number. It's a real messy number. So it's an irrational number. So on our list of notes, we're going to list pi as an irrational number, okay? These are decimals that do not end. That's if you want to wait it. They do not end, nor do they repeat. So they're kind of like the exact opposite. Remember, you're either rational, you're nice, you have nice endings, or you repeat the same thing, or you don't repeat nothing, and you're irrational, okay? I also want you to grab your calculator. I want you to check out. If you go below the pi key, right above the divide key, go second divide key, there's actually a number E. Now, we don't really use E a lot in our math class. We won't use it at all. But if you start compounding interest and you compound it more and more often until you're compounding it continuously, in finance, the letter E is similar to like pi. It does have a mathematical numerical value, and they use E for short. So that's also an irrational number. So pi and E. It turns out square roots of 2, okay? So I'll add that. Lots of square roots are irrational, okay? Now, not square root of 25. Now, square root of 25, that would not be irrational because that actually works out to be a perfect number 5. Square root of 2, though, if we check with our calculator, the square root of 2 is not a nice, neat number. It's 1.414, and it's got a lot of decimals after. And if you do try to say, you know, I wonder if I could change that. Let's find our math key. Change that to a fraction, enter, enter. It turns out I get the same decimal answer. There is no fraction equivalent to square root of 2. So since it can't be expressed as a fraction, okay, it doesn't have a decimal that ends or repeats, square root of 2 is definitely irrational, okay? Does not, let's see, does not express itself as a fraction. Okay, does not express itself as a fraction. So those would be irrational. Lots of square roots. If you find a number that would be like 4.28715, and then just the numbers kept going on and on again, a decimal that doesn't end or repeat is irrational. So pi, E, lots and lots of different square roots. Not perfect square roots, but other square roots. The square root, let's just say, of 1/3. The square root of 1/3, if we check with our calculator, square root of 1 divided by 3, close my parentheses, it's 0.57. If I try to change that to a fraction, it's not always perfect to do this, but at least you get an idea. It doesn't change to a fraction, so that's definitely falling under the irrational category. So, real numbers are either real or imaginary. You're either rational or you're irrational. Now I want to talk about the rational side. We're going to talk about this left-hand side. I want you to think about a box. I have seen people that will give gifts, and they have a small gift, and they put it inside a box. They put that smaller box into a bigger box, and that slightly bigger box into a little bit larger box, until they may have this gift wrapped into 4 or 5 boxes, and they carry in this huge package. It takes forever to open it. So we're going to kind of do a little bit of that. Think about the real numbers as being filled with lots and lots and lots of numbers. There's a lot of real numbers. Lots and lots of numbers. Most of the numbers in the world are real numbers. And then most of them rational numbers. Okay, a lot of rationals. But you separate them out to rationals and irrationals. Now let's take those rationals and let's basically take away all the decimals, take away all the fractions, until we just have integers. Okay, integers would be what I consider whole numbers, including negatives, 0, and positives. Okay, whole numbers including negatives, 0, and positives. So like ... -2, comma, -1, comma, 0, comma, 1, comma, 2, comma, 3, comma, ... In other words, think about a number line. These would be the numbers. These would be the big marks on the number line, not the in-between spaces. But if you fall right on those marks on the number line, you are an integer. Okay, falling on those marks on the number line. Now, remember how we're going to take these as subgroups. These are subgroups. Now, I want you to think of your integers in a box. And then I want you to reach in and take out all the negatives. So whole numbers have no negatives. So if you take out none of the negatives, okay, and let these start with 0, I'll write it on the side here. Okay, whole numbers start with 0. So basically it's 0, comma, 1, 2, 3, ... Okay, they start with 0. Take away the negatives. Now when you go down to natural numbers, there's only one number difference between whole numbers and natural numbers. Some people call these counting numbers. Okay, so natural numbers are counting numbers. When you learn to count, you learn to count with probably number 1. Your mommy probably held up a little apple or a little toy and said there's 1, then added another one, said 2, then 3. So basically you start with 1. Start with 1. So 1, comma, 2, comma, 3, comma, 4, comma, ... Keep going. So please understand, if you are, let's just say, for example, let's say I pick a number like square root of 16. Okay, technically square root of 16 could be a natural number. I could put it also in the whole numbers, because what's square root of 16? Does square root of 16 work out to be 4? Yes. So 4 would be a whole number. Square root of 16 could also be an integer. Yeah, 4 is on the number line. And then square root of 4, or square root of 16 being 4, is also rational, and it's also, guess what? Real. That one expression of square root of 16 actually falls into 5 different categories, but the very first group it's a member of is the natural numbers. If you are a natural number is also a whole number. If you're a whole number, you're also an integer. If you're an integer, you're also a rational number, and if you're rational, you're also real. So when you have these subgroups on the left, go with the smallest group that number could belong to, and then keep going up and go up. It's almost like rungs of a ladder. Go up the ladder to classify your number. Now what we did in class is I had given a lot of different numbers on little slips, and so the students had to look at their number and make a decision as to what group it best went in. Okay, and so when you go to the back to start your homework, exactly what you're going to do here. So let's do number 1. Number 1 says 17. Okay, think about 17. First of all, I notice it can be expressed as a fraction. So if I had to pick real or imaginary, well, I don't see an I, so it can't be imaginary, so it must be real. And if I think rational or irrational, well, it can be expressed as a fraction, even if we put 1 on the bottom, so it's definitely rational. If I go back and look, the number 17. If I go out here far enough in my counting, 1, 2, 3, 4, would I eventually count to 17? Yes. So 17 is a natural number. 17 is also a whole number. 17 is also an integer. 17 is also rational. And 17 is also real. If I do the right thing, I should actually check mark 5 boxes when I do 17. Okay? It's rational, it's an integer, it's a whole number, it's natural. 1, 2, 3, 4, 5. And of course, it's not imaginary. We were crossing that out. I should do 5 different check boxes because you go up the ladder on the real side. Okay. All right, 3 pi. Take a look at your notes. Where does pi show up? Where does pi show up? Anybody see pi right here? If you're a pi, you're probably what kind of number? Irrational. If you're irrational, you're also what? Real. Remember, you go up to the top. So irrational is also a real number. Okay, I'll remove my highlights. So that tells me that if I'm doing 3 pi, it's not natural whole integer, it's not rational, it's irrational, which means it's also real. Remember how we went up the ladder? All right, now let's do negative 13. Negative 13, well, I could express negative 13 under 1, so I know it's definitely going to be a rational number, which means it's definitely real. It's on the number line. Now let's go look and see if it's anything else. Negative 13. Well, if right here in the integers category, if I went back, would I be at negative 13 at some point on the number line? Sure would. Sure would. So it's also an integer. It is not whole number because I can't be negative, but it is also an integer. So in number 3, you should have integer, rational, and real all picked out. Okay, I want to do 2 more with you. Number 4, negative 16. Now, I don't see an I, but I do see square root of negative 16. Square root of negative 16. All right, let's do square root of negative 16. All right, square root negative 16. Hopefully you already know what this is going to be. Square root of 16 is 4, and the negative comes out as an what? I. Remember, we do have it on in imaginary mode. So if it's got an I in it, where does it fall? If it's got an I in it, where does it fall? Numbers that must contain an I must be what? Imaginary. Do you go up anymore? Is it also real? Nope. Remember, if we go back over here to our very first concept map, if you're imaginary, you're just some of the numbers, but you have to be imaginary or real. So when I get ready to mark my boxes for this one, only 1 box, and that's it. Because that's the same thing as 4i. 4i is only an imaginary number. All right, number 5. I need to simplify this just a little bit. Okay, if I take a look at the numerator, first of all, I see it's a fraction. I'm going to go out on a limb and say, you know what, rational numbers can be fractions. And if it's rational, it's also real, okay? Rational and real. Let's just make sure we see that. Rational and then real. Remember, you go up the ladder, so I want to make sure that we find that, okay? Rational and real. Now, 16 over 12, right? 4 squared is 16 because that's 4 times 4. I don't think that's going to change to an integer because I don't think it's going to divide be an even number, which means it's not an integer, it won't be whole, and it's definitely not natural because it stays a fraction. I actually think if you take your calculator, 16 divided by 12, math, fraction, enter, it's 4/3. 4/3 is not. All it is rational and real. All right, I want you to take a look at 6. I'm not going to do this one, but does square root of 9 work out? I think it does. See if you can make a determination. Again, go back over here and find the very first subgroup that it would belong to. Sometimes you have to go up the ladder. A natural number is also a whole number, which is also an integer, which is also a rational number, which is also a real number. So don't forget to do that. If you're an irrational number, okay, if you're an irrational number, you're also a what? Real number. So irrational, real, because we have those 2 subgroups. All right, I'm going to stop there. That would be the lesson on imaginary letters, imaginary solutions, and the real number system.